Okay, recording has started. Let me get the iPad in here. Okay, the iPad doesn't want to join. There we go. All right, sweet, we're in. Okay, so good morning, everybody. Welcome back to Math 115. So today, we're going to continue our discussion about inverse trig. Okay, we're going to talk more about inverse trig and about all the other inverse trig functions. Before we start, let me share the screen. And I woke up thinking about something today, so I figured that I'd share it with you before we start class, something I thought that was kind of interesting, and I always liked learning about things like this when I was an undergraduate student, and my instructors would tell me stuff like this. So I woke up thinking about the natural numbers. Which are numbers like 1, 1, 2, 3, ... These sorts of numbers, we call them natural numbers. And the reason we call them natural numbers is because they were sort of the first numbers which occurred to human civilization. Okay, it was kind of natural to start by counting on your fingers, and well, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 fingers, and that's why we count in base 10. And the natural numbers are just all of the sort of whole numbers which we can count on our fingers or on as many fingers as there are humans, and that sort of thing. And there's actually sort of a big question about the natural numbers, which is whether or not we should include 0 in the natural numbers. Okay, so is 0 a natural number? And what I thought I'd share with you is that there's actually a big divide in the mathematical community about whether or not 0 is actually a natural number. First of all, because it wasn't actually described or invented or written down until much, 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 much later. And second of all, because, I mean, just the properties of the number 0 are very, very different from the properties of all of the other natural numbers. So those are arguments why you might not include it. But some people feel like it's really the most logical thing to keep it in there. In fact, there are even professors at our own institution who disagree on this matter. So I thought I'd ask you guys before we start, do you think 0 is natural? There's no right or wrong answer here. I'm just curious to get your opinion. Heidi says no. Come on, you have to weigh in one way or another. Justin also thinks no. Anyone for yes? Another argument you might have for yes would be to say, well, the integers is the set of numbers which is like, you know, -3, -2, -1, ... in both directions, right? And 0 also, and 1, 2, ... And so this is the integers. And so one way to think about this, why we might include 0 in the naturals, would be to say, well, the integers is just all the naturals plus the negative ones. So if we just take away all the negative ones, then we'd be left with the naturals, and that'd be 0, 1, 2, 3, dot, dot, dot. Well, anyways, I just figured I would ask because I thought this was something that it seems so weird to me that, modern mathematicians would still be arguing about something like this. I don't know. I found it kind of amusing, so I figured I would ask you guys what you thought. I'm kind of the mind that the natural numbers are just the ones that we can do on our fingers, not counting 0 fingers. All right. Well, anyways, that's all I had to say about the natural numbers. Just something that I felt like I would share with the class and see what you guys thought about it. So before we started on new inverse trig stuff, let me remind us what we were talking about last time. And we started the discussion of inverse trig by discussing whether or not we thought, I can even zoom all the way down here, whether or not we thought that the sine function was 1-to-1 or not. Okay, and we decided that it's not 1-to-1. Okay, we decided it's not 1-to-1 because it fails the horizontal line test. And that caused us a problem because 1-to-oneness was a required property for having an inverse. The reason was, if a function is not 1-to-1, then it fails the horizontal line test, and its inverse will fail the vertical line test, and then therefore the inverse is not a function. So that's why 1-to-oneness matters. And we found that there was a way that we could kind of restrict our view to a smaller section of our graph. And if we just consider that small section, then it's true that the graph is 1-to-1 in that small section. Okay, so we just pick a piece of the sine function which goes from basically its most negative value here at -1 and goes then up, 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 up until we hit our most positive value here at +1. And then each y value in between is only achieved exactly once. If we were to continue this on, then all of those y values would get doubled up, right? But we're not going to continue it on. We're just going to stop right there at pi/2, and we're going to only go as far left as -pi/2. And then our function does pass the horizontal line test, and it is 1-to-1, and therefore we can make an inverse of this function. In fact, we could even go so far as to actually draw it here. If we want to draw the inverse, well, it's fine. It's going to be a function because if we draw our line y = x, and then we go back to normal pen, and then we just kind of reflect this thing across, well, what's it look like? It looks like this. Okay, perfectly fine function. It passes the vertical line test because our original function passed its horizontal line test. So in this framework, the inverse function is really okay. But we have to limit ourselves to a certain set of x values. Okay? So before, we were asking all sorts of questions about, okay, if I know the angle theta, then what are the points x and y values that are on the unit circle, which we get when we inscribe that angle theta in the unit circle? And now we're working backwards. We're going to start with a point on the unit circle. Actually, we're going to start with one coordinate of the point on the unit circle. And we're going to try to work backwards to an angle. And the reason that causes trouble is if I say find the angle theta such that p of theta is equal to something, comma, square root 2 over 2, well, then you know that sine of theta equals square root 2 over 2. But you know that this happens in exactly 2 locations on the unit circle. It happens, basically, it happens when theta is equal to pi over 4. And it also happens when theta is equal to 3 pi over 4. On both of these points, they're going to be the point square root 2 over 2, comma, square root 2 over 2. So here's negative square root 2 over 2, comma, square root 2 over 2. So the problem is when I ask you to find the angle theta such that sine of theta is equal to square root 2 over 2, you come back at me and say, well, your question doesn't make no gosh darn sense, okay? Because there's 2 points on the unit circle which have that y value, and they have different angles. So which one do you want me to pick? And I come back at you and I say, I want you to tell me the one that's on the right half of the unit circle. Okay? In other words, the value of theta should be between negative pi over 2 and pi over 2. So that's how I kind of fix my question so that it makes sense now. And now you can get rid of this other one. Okay, this other one. We're not going to consider points which are on that side of the unit circle for this question. And now you can answer my question. Okay? So that's the idea of the restricted domain and why we do that. Okay. Any questions about where we're headed with this stuff? Okay. Well, it seems like not. In any case, we've only got like 5 students in the class right now, so the probability of questions is quickly decreasing. Okay, so what we said was if we restrict the domain of sine theta to this, theta should be between negative pi over 2 and pi over 2. Then the function's 1 to 1 in that region, and so it has an inverse, and then we write the inverse function in the following way. So before we had f of x, and its inverse was f inverse of x. Now we have sine of x, and its inverse is, well, sine to the negative 1 of x, okay? This is how we write the inverse function. Okay, and it has the property that it takes as an input one of the possible outputs of the sine function. Well, the sine function has a range from negative 1 to 1, so the sine inverse function will have a domain from negative 1 to 1. And the output of our function will be the angle theta, which is between negative pi over 2 and pi over 2, such that the y value of the point on the unit circle, which is given by that angle, is our input value. Okay? That is sine inverse. Okay? Okay, and then I already kind of showed you guys this, but the graph of the sine inverse function is just the graph of sine of x reflected about the line y equals x. Okay, so in here we've got green is the regular sine function, and then the orange one looks more like, so sine looks originally like this, and our sine inverse function looks more like this. Okay, so that's how that works. Okay, so here's just another description of the sine inverse function. What does it do? Well, in words, sine inverse, the function, takes as an input a value of y such that the point x comma y is on the right half of the unit circle. Okay? And we specify anytime we're working with the sine inverse function, we're just only ever going to talk about the right half of the circle, because that way we can just kind of like forget about all of those duplicate points which we're going to have on the other side, which have the same y value. Okay, and it outputs the unique value theta such that the point on the unit circle has the y value which we were originally given. Okay, so we're given a point here on the unit circle, x. Actually, we're only given its y coordinate. So I'm putting a dot in there because I don't even know the x coordinate. But I know that there's only one point here on the unit circle, which is on the right side, which has that y value. Okay? Then sine inverse is going to return the unique angle theta, which there's only one angle theta, which is between negative pi over 2 and pi over 2, which points at that particular point. Okay, so theta should always be facing sort of to the right here. All right. Oh yeah, some notation here. Okay, here's some notation. We also write arc sine sometimes, okay? So ARC-SIN, sometimes we write that instead of sine -1. They mean the exact same thing, okay? So arc sine and sine inverse are the exact same. Okay, so let's practice this one together. We want to find the arc sine of square root 3 over 2. Okay, square root 3 over 2. So let me get some help from the students who are here today. How should I sort of begin solving this problem? If I want to know what is the angle theta which produces square root 3 over 2 as a y value on the point on the unit circle. Can anybody give me some ideas of how I might start this problem? Well, what am I given here? I'm given that the y value of the point on the unit circle is square root 3 over 2. So I should probably somehow incorporate this into my diagram. Yeah, we should definitely start on the right side of the circle if we're using arc sine. That's true. Okay, so why don't we start by just trying to draw where this point is? Well, this is a y value, right, which is a positive y value, so I can even forget about the bottom half of the unit circle. I know I'm going to be somewhere in the first quadrant, okay, since the y value is positive. And let me just put it in here. And square root 3 over 2, that's something like, well, it's bigger than 1/2. It'll be probably somewhere closer to 1. Okay, so some point here, and I don't know the x-coordinate, I just know that the y-coordinate is square root 3 over 2. Okay. Now that we've got a point inside or on the unit circle, are there any other ideas that jump out at you for what we might now proceed to do? Maybe something which we do a lot once we have a point on the unit circle. Look for its inverse. Well, yeah, we want to ultimately find that angle. That's true. So I'm ultimately interested in, well, what is the angle which points at that place? That's what I want to know. You notice anything particularly interesting about the y value, square root 3 over 2? Does it look familiar at all? Yeah, I think Heidi's on the right train of thought here. Okay. What I'm looking for here is we should do what we almost always do once we have an angle theta here pointing at a point on the unit circle. This is like screaming at us to drop a line and form a triangle. Okay? Just draw the triangle. Even if you don't wind up using the triangle in the problem, having it in there is going to help you to kind of, you know, it's only going to provide you with more information. Okay? And what is this telling us? Square root 3 over 2 is the length of this side. Why that side? Because it's the y value. The y value describes the height of the point. And the height of the point is exactly, well, if we go straight up from the x-axis to the point and measure that length, that's the height. So that length is square root 3 over 2, and we know another length on this circle. What other length do we know on the unit circle for sure? Sorry, not on the unit circle, on this triangle. We know the length of one of the other sides. We know the radius, right? The radius is always 1. Okay, this is something that I want to make sure that everybody knows, okay, is that if we draw a line from the inside of this circle to the outside of this circle, it doesn't matter where we draw it, the length is always 1. That's the whole point of the unit circle, is it has radius equal to 1. Okay, so no matter where I draw it, this length here is 1, this length here is 1, this length here is 1, and so on and so forth, okay? All of the radiuses are always 1. So when you draw these triangles, if you know one of the coordinates, one of the side lengths on one side, you automatically know one of the other side lengths, the hypotenuse, because it's always 1. And then figuring out the other one is not too hard. This one's a special right triangle, but even if it wasn't a special right triangle, we could use the Pythagorean theorem. Okay? If we have a triangle, a right triangle with sides A, B, and C, they satisfy a squared plus b squared equals c squared. So if c is equal to 1 and a is equal to root 3 over 2, then we have that b squared is equal to 1 minus a squared, which would be 3/2. No, 3 over 4, sorry. And therefore b squared is equal to 1 over 4, and therefore b is equal to 1/2 by taking the square root. So then this length here is going to be 1/2. Okay. Abdulrahman, you're not quite right with that 1 radian estimate. That's going to be pretty close. Oh, you mean 1 radius, maybe, is what you meant to say. Yeah, sorry. I think that's what you meant, was radius. Okay. Sorry. So now we have this triangle here. And remember, we want to know what is this angle which is inside of this triangle. So the side lengths of this triangle look awfully familiar. In fact, this triangle might even be a triangle which we know the angles on the inside of it. Can anyone tell me what theta should be? Not 30. 60. That's the one. Okay, so these are the proportions of a 30, 60, 90 triangle. But one thing we want to remember is that the shortest side length, which in our case, the shortest side length is 1/2. The shortest side length will be across from the smallest angle. So since 1/2 is smaller than square root 3 over 2, okay, since square root 3 is larger than 1, we know that the smallest angle here is going to be this angle up here is going to be 30 degrees. And we know the one on the bottom is 90. So by the fact that angles in a triangle have to add up to 180, we can get that this one should be 60 degrees. So our answer for what is find arc sine of square root 3 over 2 should be 60 degrees or pi over 3 radians. However you want to say it. Okay. So we're just working backwards. And I will tell you that, if you're a student in the class, it might be useful for you to make the following observation. I can't exactly ask you questions like this without a very perfect triangle here, okay? Because otherwise, you wouldn't really be able to tell, well, what should this angle be? Unless I give you a special right triangle, these problems are not really possible with the tools that we have. So if we're doing a sine inverse problem or a cosine inverse or whatever, you can pretty much, bet your bottom dollar that the answer is going to involve one of the angles inside one of our special right triangles, like 30, 60, 90, 45, or multiples of those. How did I get the 1/2 again? Well, if I have a triangle, it's a right triangle whose side lengths are square root 3 over 2, a question mark, a, we don't know what a is, and then the other one's 1 because that's the radius of the unit circle. If we have a triangle like this and we want to know what a is, we use the Pythagorean theorem. We have the following. A squared plus b squared is equal to c squared. So if I take a to be a, well, it's just a squared. B here is the side length, which is not the hypotenuse. Okay, so c, remember, c should always be the hypotenuse. And the hypotenuse is the word we use for the side, which is across from the 90-degree angle. Okay, so c is 1, and here b is square root 3 over 2. So if I take square root 3 over 2 and then square it, and that should be equal to 1 squared. So therefore a squared plus, well, if I square root 3 over 2, I get 3 over, well, if I square the denominator, it'd be 4. And that should be equal to 1 squared, which is 1. So then I subtracted 3/4 from both sides, and I got 1 minus 3/4. So therefore, a squared was equal to 1 over 4. And then I took the square root of both sides to figure out what a should be. So then I got a is equal to 1/2. Okay? If you just square root the 1 on top and square root the 4 on bottom. Okay? Does that clear things up, Sam? Yeah, so I just used the Pythagorean theorem here. Okay, or if I was really clever, then maybe I would have immediately noticed that the presence of the square root 3 here kind of seems like it's leading us towards like a 60, 30, 60, 90 triangle. And we would say, well, this looks like a 30, 60, 90 triangle where this relationship between these two looks like the relationship between the side lengths of a 60 and a 90 degree across from the 60 and across from the 90. So then the side length, which is across from the smaller one, should be half of the largest side. So then it would just be 1/2. You could also do it like that. Okay, so Pythagorean theorem always works. And special right triangles give us a shortcut. So whichever one you want to use is perfectly fine. Okay, any questions about the arcsine problem? Okay, it seems like there's no questions about the arcsine problem, so let's do another example. Let's find sine inverse of 0. Okay, so let's try this one on our own for like 2 minutes or so, and then I'll ask the class for a solution and an explanation of their solution. Okay, so try it on your own. Please do participate because it will help you learn. Just try it, see if you can do this stuff on your own. Okay, I recommend starting with a unit circle and thinking only about the right half of the unit circle. That's probably where I would start. Okay, does anybody need some more time? Maybe you could raise your hand if you want a little bit more time to work. Inside here, yeah, this is a 0 here. Is that what your question was? Yeah, that's a 0. You want a little more time to work? Okay, I'm not seeing any hands being raised, so take that as a sign we can move forward with this example. So, what do we think for this? So can anybody help me solve it? What do we think is the angle which we're going to get if we do sine inverse of 0? You can type it out in the chat, or if you're brave, you can speak up on the mic. Anyone feel like they're confident in their solution? Or anyone not confident in their solution want to kind of wager a guess here? Heidi says no, not sure about our answer. Anyone else? Sam, Michaela, Morgan, Justin? NA, okay. Maybe somebody can help me first just draw the point on the unit circle, which has a y value of 0 and is on the right side of the unit circle. Can anyone tell me where it should be? Yeah, it should be at 1, 0, right? So that's our point. Okay, this is the point 1, 0, and its y value is 0. So that's the 0 which we see here inside of our argument. And so the question is, we're doing a sine inverse problem, so our answer should be an angle theta, which is less than or equal to pi over 2 and larger than or equal to negative pi over 2, such that theta points at 1, 0. Therefore, sometimes that's the 3 dots we use for therefore, theta equals what? What angle points in that direction? Yeah, 0. 0 degrees or 0 radians. Okay, we just have an angle here which is pointing directly to the right. That angle is measured from the positive x-axis. Well, the terminal side is also the x-axis, so the angle is 0. Or you could think of 2 pi or 4 pi or 6 pi, but none of those numbers satisfy the criterion that theta is in between negative pi over 2 and pi over 2. So in this case, our answer is 0. So sine inverse of 0 is equal to 0. And it kind of makes sense if you think about it, because sine of 0 is 0. So if we flip-flop the arguments, we might expect this result. Okay? So the first line says, what is the angle theta such that if we plug it into the sine function, we get 0? The second one says, what is the y value of the unit circle, which corresponds to the angle 0? And these questions are sort of the opposite of one another if you think about it. Okay? All right. So that's another sine inverse example. Any questions about these two examples that we did? Okay, again, I think to recap, the first step is to draw a unit circle and put on it a point on the right half of the unit circle if we're doing sine. We want to find a point on that right half of the unit circle which has the y value, which is given by the argument of our function. Okay, so on the inside of that function, we get a y value. And we want to just make a point on the unit circle with that y value. And then we can either draw a triangle, or in the case of the second example, we didn't even really need to do anything. We just want to find out what is the angle which is in between negative pi over 2 and pi over 2, which points at that point. Okay, so most of the time we do that using a triangle, but in some special cases, like when we do sine inverse of 0, we're going to get 0. There's a couple other ones like sine inverse of 1 is clearly going to be, well, what's the y value? It's 1. So that's the point which is right up here on top of the circle, 0, 1. And the angle theta which points in that direction is pi over 2. So this would be pi over 2. Okay, so and so on and so forth. Maybe I'll leave that on there. Okay, so this is sine inverse. And now we're going to move on and switch gears and talk about arc cosine or cosine inverse. Okay, and there's something which you're not going to like about arc cosine. Okay, here's what you're not going to like about arc cosine. Whoops, let's move that here. Okay, what you're not going to like about arc cosine is the following. The sine function was one-to-one if we just considered the piece of it which was in between negative pi over 2 and pi over 2. However, cosine of x is not one-to-one in this region. What does it look like? It looks like this. This is cosine of x. So the issue is cosine of x doesn't pass the horizontal line test in the same region. So cosine of x is not one-to-one in the region negative pi over 2 comma pi over 2. But it is one-to-one in the region 0 comma pi. So if instead we just look at the part of cosine which goes from 0 to pi, well then that part of cosine looks like this. And if we just consider this region, then cosine is one-to-one in that region. And what's annoying about this is that the region which we have to consider for using cosine inverse is a different region than the region we have to consider for sine inverse, which is already annoying because it's already annoying to even think about having to restrict our view to a region, and now we're going to introduce a whole different region which corresponds to a different function. Okay, so there's kind of a lot of layers here going on, which is why I think this is one of the hardest sections that we'll cover in this class. Okay, but here's how it's going to work. For arc cosine, okay, we say let x be some number which is in the range of cosine. So x is one of the widths which a point on the unit circle can take, then arc cosine of x is going to return the unique angle theta such that theta points at the point x comma y on the unit circle, which is on the top half of the unit circle. So for sine, we only consider the right half of the unit circle, and for cosine, we're only going to consider the top half of the unit circle. And the reason that I do this instead is, well, for sine, if I specified a y value, well, there's 2 points which have that y value. There's the point on this side and the point on this side. Both have the same y value. But if I instead specify an x value, okay, if I specify an x value instead, but I don't specify the y value, there is another point which takes the same x value. It's the point which will be on the bottom half of the unit circle with the same x value. Okay, so I'm just using this dot as a placeholder for, whatever y is. Okay, but these 2 points have the same x value. So if you come at me and give me an x value and say, what is the angle theta which points at that x value, I'm now torn between this angle theta like this and this angle theta prime, which is here. Okay, so the issue is there's 2 answers to the question. And so I come back at you and say, well, there's 2 answers to your question. Which one do you want? And you say, give me the one that's on the top half of the unit circle. So I get rid of this other one, which is down here. I say, okay, we're not interested in that part of the unit circle. I just want to find the point on the unit circle which has that x value, and its x value and its point, this point should lie on the top half of the unit circle. Okay, so that's how we handle arc cosine, okay? So the reason we have to have this different domain of reference is because the duplicate angle, which is going to cause the answer to our question to not be really unique, the duplicate angle is going to be reflected across the x-axis rather than reflected across the y-axis for cosine, since we're talking about an x value instead of a y value. Okay, so for sine inverse, we only think about things which are on the right half of the unit circle. For cosine inverse, we only think about angles which are on the top half of the unit circle. Okay, so let's do an example. Again, we're going to do the first one together. Okay, I'm supposed to find cosine inverse of negative square root 2 over 2. So the first thing that I'm going to do is immediately draw a unit circle. And before I even begin trying to solve this, I'm going to recognize that this is a cosine inverse problem. So I should only really be thinking about what's going on the top half of the unit circle, okay? Cosine inverse should give me something in the end, which is between 0 and pi. That's what I should get at the end. So I'm going to consider angles which point in the direction which is between 0 and pi. These are the angles which I'm going to consider. And now what I need to do is I need to draw a point on the unit circle which has an x value of negative square root 2 over 2. Okay, just need to draw a point on the unit circle with that x value. And since the x value is negative, that's telling me that the x value should be to the left. Okay, so I'm just going to pick a point here and say, okay, maybe that right there is something like, this is the point square root 2, negative square root 2 over 2, comma, y. And I don't know what y is for the time being. And my end goal is to find out what is this angle, theta. Okay? I want to know what is that angle, theta. So, as always, I have a point on the unit circle, and I have a radius which is going straight to that point, and I'm trying to measure this angle theta. The number one thing that I need to do, okay, is make a triangle. Okay, this thing is just screaming at me to draw a vertical dotted line and make a triangle here. And I know this is a right angle. Okay? And I even know something about the side length of this triangle. The side length of the hypotenuse, since it's a radius of the unit circle, is 1. And this x value is negative square root 2 over 2, so I know that this distance here is square root 2 over 2. The reason I made it positive is because I'm considering it as a distance this time. So now I have a triangle one side length is 1, one side length is square root 2 over 2. What should the other side length be? Question for the class. Can we immediately find out what this other side length could be without even having to use the Pythagorean theorem? Yes, again, square root 2 over 2. This is immediately setting off flags in our mind. This is a 45, 45, 90 triangle. Okay? Square root 2 over 2 is what we get if we take 1 and divide it by the square root of 2. Or if we were to take square root 2 over 2 and multiply it by square root 2, we'd get 1. So this is a 45, 45, 90 triangle. But if you're not confident with figuring that out, you could also use the Pythagorean theorem. You'd say a squared is equal to c squared minus b squared. And therefore, a squared is equal to 1 minus, well, if I square the other one, we'll get 2 over 4 is equal to 1/2. So a squared is 1/2, so a is equal to 1 over the square root of 2, which is equal to the square root of 2 over 2. So that's the Pythagorean theorem method if you don't immediately recognize that this is a 45, 45, 90 triangle. Okay, so here's our angle. Here's our angle. We know that these two angles are 45 degrees. And there's only just one remaining subtlety of this problem, which is that we were looking for the angle theta, which is drawn in this kind of salmon color. So can anybody tell me what that angle should be? Based on what we have on the screen right now. That's right, Abdulrahman, you got it. 135 degrees. Can you tell me how you came up with that figure? That's right. 90 plus 45. Okay, so basically Abdulrahman's logic here was this angle is a 90-degree angle, and I know I need to go an additional amount, and that amount is exactly half of the rest of this 90-degree angle. Okay? The other way you could think about it is by saying, well, if I go all the way around, that would be 180 degrees, so I go 45 less than that. So this angle here is 135 degrees, or 3 pi over 4. 3/4 of the way to pi. Okay, so this is our answer. 3 pi over 4 radians. Any questions about this cosine example? Okay, seems like not. Let's try this next one on our own for 1 minute or so, and then we'll move on. Let's try to find the arc cosine of 0. So go ahead and try on your own for 1 minute, and then we'll come back as a group. See if we can figure out what this should be. All right, does anybody need a little bit more time? Please raise your hand if you want a little more time to work. Okay, Durman's got it. Okay, so we want to find arc cosine of 0. Okay, so first of all, I know that arc cosine is telling me I should be looking for an angle which is between 0 and pi. And then the 0 part is telling me that the x-coordinate of the point which is on the unit circle should be 0. In other words, it should not be left or right of the y-axis. It should be immediately on it. So here is our point, 0, comma, and I bet you could fill in what the other point should be. It's going to be 1, right? So we want to know what is the angle which is between, theta is between pi and 0, and it points directly north, kind of. Okay, so it points directly up. Well, that's going to be a right angle, which points directly up. And a right angle has measure pi over 2, like Abdul-Rahman said. Okay. For the rest of the class, did you also arrive at this answer, or did you run into some trouble? Okay. I can imagine that a student, not necessarily one of my students, but a student, could have gotten a little bit confused and thought, well, we're doing an arc cosine of 0. Last time we did an arc sine of 0 and we got 0, so maybe this is just equal to 0. But this isn't the case for this problem. Okay, in this problem, the 0 here is referring to the x-coordinate of the point and not the y-coordinate of the point. If the y-coordinate of our point is 0, then it's true. We'd be pointing directly to the right. But if the x-coordinate of our point is 0, then we're pointing directly up or down. And since we're doing arc cosine, we know the angle should be between 0 and pi. So that's how we get pi over 2. Okay. Cool. So that's how we do arc cosine. So, recapping. Arc sine. We look for an angle which is on the right half of the unit circle, for which the y-coordinate of the point is the one that we're given inside our parentheses. Cosine, we look for an angle which points somewhere on the top half of this unit circle, and its x-coordinate of the point should be the point which is given inside our parentheses. Now, inverse tangent. Okay. We're going to let x be a real number. Then, arc tangent of x, which is the same thing as tan inverse of x, returns the unique angle between negative pi over 2 and pi over 2. And this time we're using less than and greater than signs. So no equality here. Okay, so the angle will be between negative pi over 2 and pi over 2. So we're thinking about the right half of the unit circle again, such that tangent theta is equal to x. Okay, so here's how we visualize. We know that the tangent theta graph looks like this, and then after that it repeats, right? And in both directions it repeats. So if you give me if you give me basically a height, okay, and ask me, well, what is the theta value such that this height here, tan theta, is equal to the number which you give me? Okay, well, I'm going to limit my frame of reference to this region of the graph of tangent. I'm just going to consider this one copy of it, if that makes sense. Okay, or if you think about it, it's also, if we look at our unit circle, okay? Then what is it? Well, remember the tangent is going to describe the length of, well, if we take a point here and draw it like that, you know, such that this thing is tangent, well, what is this distance here? Okay, or what is this distance here? Or if we get up real far, then it'll be really, really long, right? And so on and so forth. That's the other way we can think about tangent. And then we think about points down here in this region as having sort of like a negative. We know we have AS. We know we have ASTC. So we know that tangent should be negative in this region. So we just call this length. We measure it and then we make it negative, and that's what the tangent is. Okay, so the shortest possible thing it's going to be is when we're right on the right-hand side of the unit circle, in which case we're already on the x-axis, so there's 0 distance from that point to the x-axis. And then the longest that it could possibly be would be if we were on top, in which case our line is parallel to the x-axis and it never ever crosses. So that's why we don't include pi over 2. So we're searching for a point, basically, which is on the right half of this unit circle, such that the length of that point, when we draw a line in this kind of direction, which is tangent to the circle, in that direction, the length of that line segment should be equal to our argument. Okay? That's another way of thinking about it. Okay, so let's have an example. We'll do arc tangent of negative square root 3. Okay, so I'm going to draw a couple graphs here. The first graph I'm going to draw is of the tangent function. What does it look like? Looks like this. Okay? And the meaning of this, okay, the meaning of this number here is this is the x value such that if I plug this x value into the tangent function, I get the y value negative square root of 3. So then this point here would be at negative square root of 3. So this point here would be the point x comma negative square root of 3. And I'm interested in what is the value of x. Okay, what is the value of x? Okay, the other way I can think about this is the following. I can draw the unit circle. And since I'm working with tangent, I know I should be thinking only about the right-hand side of the graph. That's not a very good highlight. Should only think about the right-hand side of the graph. Okay, and I want to draw a point which is on the unit circle whose length to the x-axis is negative square root 3. So that's telling me that since tangent is giving me a negative value as an output, I should be in quadrant 4. So I'm actually going to just consider this region. And I'm going to consider a point here. The point here is x comma y. And we have that this length here, which goes to the x-axis, is square root 3. In other words, we have an angle theta which points down at this thing. And we know that tangent of theta equals y over x equals negative square root of 3. Okay, equals negative square root of 3. And our goal is to find out what that angle theta is. Okay, so here's how we can think about this. As usual, I'm going to complete this triangle here and see if we can think hard about the way this triangle is going to work. Okay, so here's the angle theta, and we do know one of the side lengths is 1. Okay, the only problem is now since we're talking about the tangent, rather than knowing immediately what one of the other side lengths is, and so that I can just get the third one, well, instead of giving me one of the lengths of the other two sides, they tell me instead the ratio between the side lengths of the other sides. So we have the following. We have a triangle here. It was such a bad triangle that even Notability couldn't fix it. Oh, come on. Be good. There we go. We have a triangle here. We're interested in this angle theta. We know this is a right angle. We know that this length here is 1. We know that this length is A and this length is B. And we know that oh, why don't we just call them X and Y? We know that this length is X and this length is Y. And we know the following. Y divided by X should be equal to the square root of 3. Okay, the reason I'm using a positive now is because Y and X are distances when we're thinking about it as a triangle. Okay, when we're thinking about it as a triangle, we're considering these distances. We know that Y divided by X is equal to the square root of 3. Or I can think about it in the following way. Y is equal to the square root of 3 times X. So what does that tell me? That tells me I have a right triangle. And the way I get the length of y is by taking the length of x and multiplying by the square root of 3. Does that remind you of anything in particular? If we get the side length of another side of a right triangle by multiplying by the square root of 3, very good, Abdul Rahman. That should get us thinking about 30, 60, 90 triangles. Okay. Oops. In a 30, 60, 90 triangle, if this side is x, then this side will be x times the square root of 3, and this side will be 2x. And basically, this is the situation that I've got over here. Okay, if this is the 60, this is the 90, and this is the 30. Okay, so this is the situation I've got here. I know that the relationship in my triangle on the right-hand side has the same relationship between x and y as this triangle has relationship between x and x times the square root of 3, because guess what? These two things, x times the square root of 3 and y, are equal. Okay, so if this side is then 1, what should then the length of x be? Want to know, what should the length of x be? This is what I want to know. If this side length is 1, what should the length of x be? Yeah, 1/2. And then y should be equal to that number times the square root of 3. Okay, and then I can sort of see now that this angle, which is in here, is actually the angle. Well, I know that this angle inside the triangle is 60 degrees. Okay, but that's if I measure the angle in this direction. Okay, so the direction here is that I'm measuring this angle is from here to here. If I'm instead inside my circle and I'm measuring the angle in the opposite direction, then we will get that theta should be equal to negative 60 degrees. Or negative pi over 3. Okay. So that is how I find the tangent inverse of a value. Okay. It takes a little bit more subtle thought to make it through this example on account of the fact that we weren't given what the length of one of the sides was. We were just given the ratio between the two sides. But if they tell us about the sides of a triangle and they say that one of them is equal to square root 3 times the other one, I think actually we had y is equal to the square root 3 of x times x. Then this is screaming out, if we have sides of a length of a triangle which satisfy this equation, well, this is begging for an application of 30, 60, 90 triangles. And if we have instead something like y is equal to x, then this is telling us, well, the side lengths are the same. So then this is a 45, 45, 40, 90 triangle. Okay. Or if we had y is equal to x divided by the square root of 3. This is again telling us this is 30, 60, 90 triangle. And so on and so forth. Okay. that's all I have to say for today. If you guys have any questions, please hang around. I can stick around for a few minutes after class and answer them. Otherwise, have a great weekend. Don't forget you have homework due, you have exit slips due, and there will be an exam on April 8th. But that's a ways away, so. Okay, have a great weekend, everybody. If you have questions, go ahead and type them out in the chat. Otherwise, peace out. Or you can open up your microphone if you want to ask questions as well.